Suppose a particle is moving along a path from some starting point, initial point A, and traveling along the path, we'll name the path C, to some terminal point B, and it's obviously comes with this orientation that's moving from A to B. And as the particle moves along the path, it's being acted on by some force field, and the force field, or the vector field, is defined at every point along the path. Okay, so I'll just draw some vectors here along the path, and in general this vector field should be defined on some open neighborhood that contains the path and not just along the path itself, but all we're going to care about is that it's defined along the path, and we want to know what is the work done by this vector field on the particle as the particle moves along the path. So we might remember from Calculus 1 or maybe a physics class that work is equal to force times distance. Okay, but this is the one-dimensional version where the force is just a magnitude. It's a magnitude that could be negative, so that's where the direction is factored in. But in other words, it's not a vector in the sense of a two-dimensional vector like we have right now. So what we have to do is we need to find out how much of this force at each point is acting on the particle in the direction of the particle's motion. And so there are some more vector fields happening along this path of this particle. In particular, the particle's moving, okay, and so one assumption that we should make is that this path is smooth, and so r dot is not equal to 0 at any point along this path. So that just tells us that our particle isn't stopping to take a break as it moves along this path. It's moving the entire time. So that's one assumption, and if that assumption is true, then r dot is actually a vector field along the path. It's the velocity field along the path, and if we have a velocity field, then we can draw the unit tangent field at every point. So remember, the unit tangent vector field is the vector field of vectors that all have length 1 and point in the direction of motion. So these are our vectors t. Now you're going to have to, based on my drawing, pretend that these have length 1. But the idea is that they just pick out the direction of motion of the particle at every point. And then the force field itself only acts on this particle, or in terms of the work, it's only contributing to the motion of the particle in the direction of that tangent vector field. So what we need to do is project our force onto the tangent vector field, and notice this one that I'm drawing right here is going to have to be pointing the opposite direction for the projection. So there is a negative contribution by the force field in some sense. And as I draw this picture, think about what we're going to have to do to actually compute the work. Well, I'm going to call this new vector field the projection vector field. I'll call it P, because that's exactly what we've got here, right? And we've projected these vectors onto the direction of motion. And so P is equal to the vector field, which is the projection of F onto T. Okay, so remember the formula for projection then is this is T dot F over T dot T times T. All right, but the tangent vector field is a unit vector field. And the unit vector field tells us that the length of T is equal to 1, right? Length of T is equal to 1. And so this dot product in the denominator does not contribute, and our vector field is just equal to T dot F, that's a scalar function, times T. Okay, but again, in our one-dimensional situation, what we really want to do then is add up at every point. If we zoom in enough, we have our unit tangent vector field is in the direction of motion. If we take a tiny little segment of arc length now, so at every point nearby we look at a tiny piece of arc length, okay, a little piece ds of arc length, then the work done nearby is approximately equal to that tiny piece of arc length multiplied by the magnitude of this force, if we allow for a negative force for like this situation right here. Then what we have is that we want to really integrate up the scalar projection of this P with respect to arc length. So that's our function, right? And so what we're going to do is, if we remember, t is a unit vector field, right? So the scalar projection is just equal to this, t dot f for this function. Okay? In general, the scalar projection, we'll call it p without a hat here, is equal to t dot f over the length of t. And like we said, the length of t is just 1. So it's just t dot f for this situation that we've set up here. So to compute the work, we could write out a Riemann sum argument here. I believe there's one in the textbook, so I encourage you to look at that. But I'm just going to write down the integral. We want to integrate up the scalar projection of the force, t dot f, with respect to arc length. So the total work done by this force field on this particle as it moves along this path, so it's very specific to this situation, right, is the integral along C of t dotted with f times ds. And actually I'm going to switch the order of this and write this as f dot t times ds. And the reason that I'm switching the order is because actually we can simplify this situation even more. Let's remember what t is. Well, t, we talked about this a minute ago. It's equal to the velocity divided by the speed. Okay, so t is equal to r dot divided by length of r dot. And we also know that ds, this is a tiny change in speed, right? This is equal to the speed, r dot, times dt, tiny change in time. So if we put this all back together, what we end up with is the work, the total work, which I'll just call w, is equal to the integral along C of, now notice the parameterization is now playing a prominent role, and the assumption that we made that r dot is not 0 is also very important, because at this point we've got an r dot, length of r dot in the denominator, and what we end up with is our integral for work is f dotted with r dot over length of r dot. This dot on the r is the derivative, right? Times length of r dot dt. Okay, but since r dot is not 0 and it is a scalar function, it can be factored out of this dot product and then canceled, numerator denominator. Okay, and we end up with this formula, integral over c f dot r dot dt for the work. But at this point you might remember that r dot dt, this is just the differential. It's a vector though. It's a differential vector of r. So if our r, for example, I'll draw a little line here so we can write this down. But if our vector function r is in 3 dimensions, x, y, z, then its differential is a differential vector actually. dr is the vector of differentials, dx, dy, dz. And based on the way this is computed, each of dx, dy, dz are equal to, we did this in a previous example, x dot, y dot, z dot times dt for each one of them. That can be factored out. And at this point, this is just the vector r dot. So dr is equal to r dot dt, and then look at that. That's exactly what we have, right? And so from now on, what we will write is that the work done by a vector field or a force field on a particle along a path is equal to the path integral f dot dr. Okay, so this is a formula for the work done by a vector field on a particle along a path.